Hi everyone, how are you doing? Welcome to the course Machine Learning Fundamentals with an emphasis on deep learning. In this course, you'll learn how to solve problems using machine learning. You'll learn how to do useful stuff. You'll learn how to apply machine learning techniques for your own projects, for your own applications. And you'll discover that you don't need to be an expert in machine learning to do this. You don't need to be spending 1,000 hours learning machine learning in order to do some useful stuff in machine learning. Even with a few hundred hours of work, you'll be able to do useful projects. If you were to take this course prior to 2000, you would probably be learning this set of topics. Symbolic rule-based systems, they're where a human expert writes rules, and there's a computer developer that converts those rules into some computer code. So we might have a human expert in language, a linguist, write rules on how you would translate from one language to another to do a machine translation system. Naive Bayes' statistical method. Matrix factorization is a technique often used for recommendation systems. It still has a place there, but it was really hot in pre-2000s. Regression analysis, support vector machines, they were really big back then. Decision trees, which have a place even today. And finally, hidden Markov models, which were really useful for doing machine translation. The bulk of machine translation systems were probably hidden Markov models, and especially useful in speech recognition. So that was the landscape of machine learning around 2000 or so. Around 2015, this idea of having human experts do it kind of died out as an idea, and in its place, other algorithms were more prevalent, like small neural networks, the thing kind of on the bottom of this list. Neural networks were big in the 1960s. There was an influential paper then that said, there's limits of how good these neural networks can be. And that paper created kind of the neural network winter, I guess you could call it, where there was a lack of funding. No one was willing to fund this research in what looked like a field that didn't have potential. But in 2015, or even before that, there's always been a steady growth in this idea of neural networks. So here you see on the bottom the amount of data available, starting in 1990 when relatively little data was available, to 2010 where a lot more as the internet became more and more prevalent. In 1990, if you were trying to do an Arabic to English machine translation system, it was doubtful you could find data for that. So you might want to have a reliance on human experts to help you. But by 2010, there were a number of newspapers that were Arabic newspapers that had the articles both in Arabic and in English. You could use that to have a computer analyze and generate a machine translation system. So as more and more data progressed, the performance of these algorithms improved. So support vector machines, small neural nets, random forest, and naive Bayes, their performance improved as a consequence of having more and more data. And that improvement far expanded or was much greater than the slight differences among these different algorithms. So what happened between 2010 and 2020 is that there was this exponential explosion of data. If we thought there was a lot of data available in 2010, the amount of data today is humongous. So what happened to the performance of these algorithms? We would predict that as we got more and more data, the performance would improve. But what in fact happened was that at some point, the more data we threw at a support vector machine, it didn't improve the performance that much. It kind of plateaued. So most of these methods that were big back then just plateaued. It didn't improve as we got more and more data. And what did improve were large neural networks, this idea of deep learning. So they could handle the large exponential data, whereas other algorithms could not. So that created this big bang in machine learning. The first aspect of the big bang that created it was just having large amounts of data, that big data that we just talked about. The second was the huge improvement in hardware. Instead of running stuff on a CPU, on the chip that's in a common server or a laptop, we instead relied on the performance of graphics cards. For example, this NVIDIA Tesla V100 from a few years ago, you can see it has 640 tensor cores, 5,000 CUDA cores, so a very parallel system that could really process lots and lots of data at high speed. Things we can't do on our laptop, we can do easily on a graphics card. Add these graphics cards together, like 27,000 of them, and you get the world's fastest supercomputer. So now we're relying on graphics cards instead of kind of the traditional chips that powered, the laptops forever. So that was the second aspect of the Big Bang. The third aspect was what's called deep neural networks. And by deep, I mean the number of layers. And by a layer, I mean each of these vertical columns. So in this very tiny example, we have 3 nodes in one layer, but we have 1, 2, 3, 4 layers. Now, once we got big data and GPU, we could develop much larger, more improved algorithms that could be much more accurate. Their performance was far greater. So one image classification system, the VGG19, had 19 different layers. So we could get what's called deep neural networks, deep, large number of layers. So that was the Big Bang in machine learning, the huge explosion, the huge improvement in artificial intelligence, self-driving cars, huge improvement in machine translation, huge improvement speech recognition. You name it, the improvement was because of this Big Bang and these deep neural networks. So now 2 classes of algorithms dominate the landscape. Before there was 5, 6, dozens of algorithms people could choose from. Now the sensible thing is really there's 2 huge ones and there's niche reasons to use some others. The first one we've already mentioned is deep learning, and you've probably heard about this in the popular press. The next one is XGBoost. It works well for column type data, for highly structured data. Since that's one's not in the popular press, let me just give you a few quotes. So here, this person who won the Liberty Mutual property inspection competition said, "I only use XGBoost." In general, there's this comment, as the winner of an increasing amount of Kaggle competitions. Kaggle is a site for data science. They obviously host a number of competitions. They say XGBoost showed us again to be a great all-around algorithm worth having in your toolbox. The only supervised learning method I used was gradient boosting, as implemented in the excellent XGBoost package. And then finally, when in doubt, use XGBoost. So we're going to cover that as well. So again, before, if you took this course 5 years ago, 8 years ago, you'd cover a host of algorithms. Now you can focus on a few and really account for most of what you need in order to do useful stuff. So in this course, we'll spend about 20% of our time kind of looking at the fundamentals of machine learning, explore some of these other algorithms just in passing, just to gain some familiarity with technique. 25% of our time will be spent on XGBoost. XGBoost is a smaller family of algorithms compared to deep learning, so we'll spend less time on that. And then we'll spend the bulk of our time on deep learning. And we'll explore one interesting aspect of deep learning called generative neural networks. We'll be using what's called Google Collab. It's a free service that allows us to do stuff on a GPU. If we tried to run an image classification system on our laptop, man, it would be lethargic. It would be really slow. It might take us days to do stuff. Google Collab will be much faster. It's free. It's an awesome service that Google provides. Here's the list of what things you'll be learning in this course. You'll learn how to architect a scalable machine learning pipeline, kind of big words, but that really means that you just don't take the data and plug it into an algorithm, but there might be some pre-processing involved. You might pre-process text in certain ways to get it in an input in a form that you can use in your classification system. And on the other end, you might want to have some, after you've done that, run the machine learning technique, you may need to evaluate how well it does or tune up the algorithm. So we'll learn kind of how that's all put together. You'll learn to run machine learning jobs on a GPU with Jupyter notebooks. These are really common techniques for people exploring machine learning, even in industry. So we'll use those techniques. We'll learn to evaluate different machine learning models. How do we determine if this algorithm works well with these different parameters? And based on that, we'll determine which algorithm to use for which application. So if we have a specific application, which algorithm will be the best one to use. Some data sets, some problems have large amounts of large dimensions. Large amounts of dimensions, large dimensionality, I'll call it that. And we'll learn techniques to reduce that so our algorithms can run a little bit more efficiently. We'll explore some simple techniques at first, just to kind of get grounded in how things work, and those are the linear models, so we'll use those. And finally, we'll learn kind of the lingo, how to communicate with other people about machine learning problems. At the XGBoost level, we'll learn how to apply decision tree algorithms to create a classifier, so we'll learn about entropy, how decision trees work. We'll learn how to combine trees, these decision trees, into what's called a random forest to improve performance. We'll kind of generalize from that, look at a way of combining weak classifiers into a number of weak classifiers into a strong one. So if you have one person telling you something and you have 10 people telling you the same thing, your confidence about what they're telling you, it increases as you get more and more people. So it's kind of the same thing if we're using kind of independent algorithms. So we'll look at that. And finally, we'll focus in and look at this XGBoost algorithm. On the deep learning side, we'll first start with a real simple example of building an image classification system. We'll go back in time and kind of look at, well, how does it really work? What are the different parameters we can use? Understand a little bit about the mathematics behind it as a way of being able to intelligently alter the algorithm to improve performance. We'll look at one aspect of deep neural networks called convolutional neural networks. They're really big for image classification as well as text classification. So we'll look at those, and we'll also look at how to build deep learning models to handle text. So what skills am I assuming that you have? Well, I'm hoping you have a little bit of knowledge in Python. And if you don't have that, at least I'm hoping that you'll be skilled in a programming language. If you're skilled in a programming language, you'll probably do fine with what's presented here and be able to kind of rapidly gain, the stuff that you're lacking. We're using 2 standard data science libraries, NumPy and Pandas. So if you have skills in those, thumbs up. You should be off to a great start in this course. If you're expecting that, building algorithms from scratch, so take the Python code, raw Python code and expand it out to this algorithm, that's not what we're doing. We're not building things from scratch. In 2010, we did build things from scratch. Now there's libraries. People have done it for us in a very effective, efficient, high performance way. So ways where an algorithm can run on a graphics card that has 5,000 nodes. So 5,000 cores. So it'd be tough for us to do, but people have done it. We're going to just learn how to piece things together to create our system. I wanted to keep this intro short so we could get started on the important stuff of let's get going and understand a little bit of theory and start coding away. So I hope this was helpful. Welcome to the course. Hope you have a good time. Bye.